Alright, today we're going to start Chapter 9, and so for the next month and a half, at least 2 months maybe, we're going to be doing trigonometry. So just a little background on trigonometry. In general, it's just a relationship among the sides and angles of triangles. It doesn't have to be used in triangles, but that's commonly what we use it for, or where we see it. It's used in astronomy, navigation, surveying, sound waves, rotation and vibrations, light waves. So those are just some examples of where we see uses of trigonometry. There are two ways to find the measure of an angle, which we're going to look at today. One is in degrees, one is in radians. The radian angle measurement is more commonly used, well, maybe not more commonly used, but it's definitely more commonly used when we're dealing with calculus. And then usually angles are denoted by Greek symbols as opposed to our standard alphabet. Usually we use the standard alphabet for side or length measurements and Greek symbols for angles. Now this is not always the case, but this is just usually the case. So symbols such as alpha, beta, theta, those are common symbols used for angle measurements. Alright, so specifically we're going to start with section 9.1 today. We're going to look at angles in degrees and radians. We want to understand the standard form of an angle and be able to convert between radians and degrees and approximate angles in radians and degrees. Okay, so the first thing we're going to look at is sketching an angle in standard position. Well, what does it mean to be in standard position? An angle is in standard position if the initial side, which we're going to look at in a second, is on the positive side of the x-axis. So if I take my coordinate axes here and I sketch some angle like this, here this is the initial side and this is what we call the terminal side, and then we have vertex of the angle, and that's going to be right here. So this is an angle in standard position. Just to show you an example of an angle not in standard position would just be an angle in space. So if I sketch something like this where I have to draw a direction of the angle, now I would say this is my initial side, and here is my terminal side. And then the vertex is this point right here. So you can see though that through a rotation I could make this an angle in standard position. So we want to understand that when we're talking about an angle in standard position, that what we're talking about is the initial side is on the positive side of the x-axis. Okay, so now let's look at positive and negative angles. So when we draw an angle, we can have many different representations of that same exact angle. So positive angles are measured counterclockwise. So if I draw some angle here, this would be a positive angle, let's say alpha. Negative angles are measured clockwise. So if I draw a similar, or I'll try to draw kind of the same angle, I draw this, but now I measure in this direction, this would be a negative angle, and I could call that, let's say, beta. This leads us to the idea of coterminal angles. So coterminal angles, this is a very important concept here, are angles with the same initial and terminal side. So what this leads us to is there's an infinite amount of ways to represent the measure of an angle because it has an infinite amount of coterminal angles. So, for example, if I draw, let's say, this angle here. So if I have, this is some alpha. Well, I'm not restricted to just going around once. So I could draw, well, let's see, the negative angle would be beta. And I could also do this. So let's call that theta. And I can continue on with more examples as well. Basically, I can keep starting with the same initial side. I can keep going around in a circle and stopping at the terminal side, both in the positive and negative direction. So you have an infinite amount of coterminal angles. Okay, so we have two forms of measure for an angle. Those are radians and degrees. So what is 1 radian? Well, 1 radian is the measure of a central angle theta that intercepts an arc I'm going to call the arc S, equal in length to the radius r of a circle. So, okay, what does that really mean? Well, what that leads us to is an equation. And that equation is theta equals S over R, where theta is an angle measure in radians, S is an arc length, and R is a radius. So if we want to see a picture of something like that, it would be, so this would be S, this would be theta, and this would be R. And so that's the relationship between an angle in radians, an arc length, and a radius. So now if we manipulate this equation a little bit, so let's solve it for S, I know then that arc length equals theta times the radius. Okay, well what if the arc length is all the way around the circle? Well, then we would call it circumference. And if this is circumference, then I know it equals 2 pi r. And so this leads me, or this proves to me that 1 revolution is 2 pi in radians. So we want to make sure we remember from the beginning of the year when we were doing our review that radians don't actually have a symbol like degrees do. So if an angle is not specified to be degrees, we just assume it's radians. Okay, so now what is 1 degree? Well, 1 degree is equivalent to 1/360th of a complete revolution about the vertex. And that should actually make sense because we know there's 360 degrees in a circle. And so now we want to point out some of the relationships between radians and degrees. So if I know 2 pi is 1 revolution in radians and 360 is 1 revolution in degrees, I know that 2 pi equals 360 degrees. Therefore, I know pi equals 180 degrees. I know that pi over 2 equals 90 degrees. And I know that 3 pi over 2 equals 270 degrees. And so then this leads me to my conversions. So how do I convert from degrees to radians? I multiply the degrees by pi over 180. And to go from radians to degrees, I multiply the radians by 180 over pi. So I want you to pause the video, take a minute, and convert these degrees into radians and the radians into degrees. Okay, so hopefully you got that 135 degrees is 3 pi fourths, negative 270 degrees is negative 3 pi halves, 9 pi halves is 810 degrees, and negative 13 pi 60ths is negative 39 degrees. Okay, so now in the next few examples we're going to look at making sure we really understand how big or how small angles are and where they're located. So for these 3 angles here, we want to first determine what quadrant is the angle going to be in, and by quadrant we mean in standard position, so we're talking about where's the terminal side of the angle. And then I want you to do a general brief sketch of the angle. So again, pause the video, determine the quadrant, and draw a sketch, and then unpause it when you're ready to check. Okay, so hopefully you understand 285 degrees is going to be in quadrant 4, negative 332 degrees 50 minutes is in quadrant 1, and negative 3.4 degrees is also in quadrant 4. So then here are the sketches that I did. Again, we're not looking for perfect accuracy here, but we're looking for a general idea. So this is 285 degrees approximately, this is approximately negative 332 degrees 50 minutes, and this is a very tiny angle, approximately negative 3.4 degrees. Alright, now I want you to do the same thing, but here I'm giving you angles in radians. So you have pi fifths, 7 pi fifths, negative pi twelfths, negative 11 pi ninths, and over here you have negative 1, positive 2, 5.8, and negative 4.5. So determine the quadrant in which each of those is in, and then do a sketch of that angle. So pause the video and unpause it when you're ready to. Okay, so here, pi fifths, I know that that's in the first quadrant. It's going to look something like this. 7 pi fifths, I know that's larger than pi, but not quite to 3 pi halves, so that's going to be in the third quadrant. It looks something like this. Negative pi twelfths is a very small angle in the fourth quadrant. Negative 1 is going to be in the fourth quadrant as well. Positive 2 is going to be in the second quadrant. Remember how I'm getting these is you want to think about, well, what is pi as a number? Pi as a number is 3.14 approximately, so I know this is less than that, but it's greater than pi over 2, which is like 1.57. 5.8 here is going to be in the fourth quadrant, and then negative 11 pi ninths is going to be in the second quadrant, and negative 4.5 is also going to be in the second quadrant. Okay, now I want you to look at the example, at the angles that I've already drawn here, and I want you to approximate each one to the nearest 1/2 radian. So this is an approximation. Yours might be slightly different than mine, but look at each one of these, come up with what you think it is, pause the video, and then unpause it when you're ready to check. Okay, so here I said that this is approximately 4 radians, this is approximately negative 4 radians, this is approximately negative 1 radians, this is approximately 5 radians, this is approximately 1 radian, and this is approximately negative 3.5 radians. If you're within 1/2 of a radian of any of all of my answers, then you're doing this correctly. Again, it's just an approximation. Okay, so we're running out of time on this video. There's a couple more examples I want to do, so we'll see those in part 2 of day 1.